Today we're going to talk about population ecology. The goal of this video is to model the growth of populations and explain the concept of carrying capacity. First, what is a population? A population is a group of organisms of the same species living in the same place. Population ecology looks at how this group of organisms of the same species living together interact with other organisms and their environment. The first concept I'll introduce you to in population ecology is population density. Population density measures the number of individual organisms living in a defined space. This can be affected by birth, immigration with an I, death, and immigration with an E. For immigration with an I, think of the word in, like organisms are moving into a space. For immigration with an E, think of the word exit, like organisms are exiting a space. Birth and immigration with an I result in a high population density because both result in more organisms living in a limited space. Death and immigration with an E result in a low population density because both result in less organisms living in a limited space. Population density is very easy to calculate, so that's what I'm going to show you how to do next. You just take the number of people in a defined space and then divide that by the land area of that space. So for example, I have a box here. Let's say this box represents a piece of land that is 5 miles in length and 2 miles in width. So the first thing I need to do is calculate the land area. The land area is just equal to the length times the width. So that would be 5 times 2, which is 10. So the land area here is 10 square miles. Now you count the number of people living on that piece of land. Say it's 20. You then just plug the numbers into your equation. 20 people divided by 10 square miles gives a population density of 2. Now, individuals in a population die, and mortality is a measurement of the rate of death in a population. You can graph patterns in mortality using what's called a survivorship curve. This is a graphic representation of mortality patterns. It shows the number of individuals in a population that can be expected to survive to any specific age. There are 3 types of survivorship curves. Type 1 shows late loss and heavy parental care. By late loss, I mean the organisms in the population live relatively long lives before they die. Species in this type of population tend to have fewer offspring and lots of parental care. Populations of humans and elephants are a good example of this type of survivorship curve. Type 2 shows constant loss. By constant loss, I mean organisms in these populations die all the time, and mortality is unaffected by the age of the organism. So some die when they're young, some die when they're middle-aged, some die when they're old. Populations of birds and rodents are good examples of this type of survivorship curve. Type 3 shows early loss. By that I mean many organisms in the population live relatively short lives. Also, lots of offspring are produced all at once, and many die right away because there is little to no parental care. Populations of fish and mosquitoes are great examples of this type of survivorship curve. The next concept I want to introduce you to is population dispersion. Dispersion is the spatial distribution of organisms in a population, and there are 3 possibilities for dispersion. It could be random, uniform, or clumped. If random, some organisms are close to others and some are not, and there aren't necessarily any groups. If uniform, organisms are equally distant from each other and there aren't groups. But if clumped, then organisms are in groups, with members of the group being very close to one another, but the groups themselves being far away from one another. Let's finish up by discussing population growth. Population growth can be exponential or logistic. If it's exponential, the population grows without limit. It just keeps growing and growing. But if logistic, the population grows quickly at first and then levels off. You can see the line go up in this graph, but then flatten at the top. Now, most natural populations show logistic growth. Examples would be fish, rabbits, trees, and so on. The theoretical maximum population that a given environment can support is called the carrying capacity. The dashed line in the graph shows the carrying capacity, and you can always identify the carrying capacity in a graph like this by finding where the line levels off after you've seen a period of growth in the population. So, why would there be a carrying capacity at all? That's because there are limiting factors. These are aspects of the environment that limit the size that a population can reach. Limiting factors can be biotic, like living things, or they can be abiotic, which would be non living things. Living biotic factors would be processes involving living organisms like competition, predation, and disease. Limiting abiotic factors would be things like changes in climate or natural disasters like a forest fire or flooding. Limiting factors can also be classified as density dependent or density independent. Density dependent limiting factors have a bigger impact on more dense populations. So these are factors that can be triggered by an increase in population size and thus crowding. Examples would be competition, predation, parasitism, and disease. If a population has a high density, it's more impacted by these factors than a population with less or lower density. Density independent limiting factors regulate population growth regardless of its size or density. Nearly all species in an ecosystem are affected equally by this type of limiting factor. Examples of density independent limiting factors would be weather changes, pollution, and natural disasters. So, whether the population density is high or low, these limiting factors equally impact both. So, to sum up, you've seen how to measure population density and identify patterns of population distribution. You've also seen how limiting factors can impact the growth of a population and determine its carrying capacity.